I needed to attend several meetings to make greetings to the faculty members.
I see. So
It's
quite formal things. Very formal.
for very formal, yes.
Well, no, it's great that you're there.
Uh,
So I think you're slightly you have slightly longer than yesterday's presenters. I think you have 15 minutes altogether.
yes,
So yeah,
including I think the question will be after the talks.
that's right. Yes.
That's after the
Yeah,
focus.
I'll just give you 2 minutes warning, and then 'cause we'll try and keep to time so we can have all the discussion session at the end. Yeah.
Michael,
Okay.
one thing that worked well was to take like a few questions just after the talk.
Oh, straight away.
But
Is
you
that
can
like points of
decide-
clarification?
Yeah, like a very quick question. But you can decide whatever you feel you want to do. But I'm just saying that's how the
Yeah.
did it yesterday. Very quick questions and then a longer discussion later.
Yeah.
Today we actually have more time for discussion because yesterday there were 2 sessions.
Yeah.
And today we have just the 1 session in the morning.
That's right. So we're not so restricted, other than
We're not so restricted.
people have dinners to go to and things like that. That's all.
Yeah, I think it's post. Yeah, that's right. Some Europe, there is dinner. Yeah, India and all it's post dinner, and we are post breakfast. I already got some emails from people on the West Coast saying it was too early for them.
Oh no.
How do you accommodate everybody on this?
Yeah. That is a challenge. Okay, I'm sure we can accommodate that then. Okay, we'll try and start on time, so just another minute, Kosuke, and then we'll set off. Do you want to make any announcement yourself? Because you're going to do the discussion session later, aren't you, at the end?
Yeah, maybe I can just say one thing about, I got some emails on discussions.
Yeah.
Yes, we can start. Good morning, everyone, and here it's morning. Some places it's night. But welcome to the second day of targeted questions on strange metals. We want to continue the discussions yesterday, which were really wonderful. Many of you had questions about the talks yesterday, and we will have occasion to ask them at the end of today's session. So hold on to them. Many of you are back, and the speakers are back from yesterday's session, so that there will be lots of time today to discuss. And with that, Nigel, please take it away.
All right, thanks, Nandini. Yeah, so good morning, afternoon, evening to everyone. There are 4 speakers in this session, so let's crack on with the first one, which is Kosuke Ishita from Todai, and all yours. The floor is all yours.
Thank you, Nigel, for the kind introduction. And good evening, everyone. So greetings from Tokyo. So I'm Kosuke Ishida from University of Tokyo, and I just moved from Tokyo University and started a new position here from this April. So before starting, I would like to thank organizers for inviting me this interesting discussion circle, and I learned really a lot from yesterday's discussions. So In this session, I think we will discuss the non-coupled superconductors experiments. So from me, I will show you the result of iron-based superconductors. It is about the extended strange metal regime beyond the pure nematic QCP. So my talk concerns particularly with the one of the target question in this discussion. So does the strange metal behavior only occur near a quantum critical point, or does it represent an extended phase? So this is a collaborative work between experiment and theory, and we have performed a high-field experiment in ISSP University of Tokyo. And we also had theoretical input from Andrew Hardy and Aavishkar Patel. So I think it is widely acknowledged that quantum criticality has been an important issue in strange metal physics. The strong quantum fluctuations at QCP reach the superconducting dome around it, and it can also act as a bosonic fluctuation, driving strange metal behavior in the funnel-shaped region above QCP. In particular, as studied in couplets and heavy fermions, the central topic of quantum criticality has been that of anti-ferromagnetic order. So the impact of quantum spin fluctuation to strange metal behavior have been well studied so far. So my question is whether the nematic fluctuation can drive the strange metallicity. And this would be a fundamentally important issue because nematic fluctuations has distinct characters from, for example, antiferromagnetic fluctuations. So antiferromagnetic fluctuations scatters the electron on the ferrous surface with a finite wave vector Q. So this fluctuation affects the fermions on the hot spots, which are connected by this wave vector. But on the other hand, electronic nematicity, I want to argue here, breaks the rotational symmetry while it preserves the translational symmetry. So this is the ferrotype long-range interaction. So this nematic fluctuation distorts the fermi surface like a Pomeranchuk instability rather than it scatters the electrons. So nematic fluctuations, in this case, all the electrons except the cold spots coupled to the fluctuations. And indeed, several theories so far have predicted that the nematic fluctuation can lead to strange metal behavior, but it is much less experimentally studied compared to the antiferromagnetic case. To address this point, iron selenide is a key material. This compound displays an electronematic transition at around 90 Kelvin, but there's no long-range magnetic order or any other intertwined orders down to zero temperature. So let me say the iron selenide possesses a pure electronic nematic phase. This pure nematic order can be controlled by several ways. For example, by applying hydrostatic pressure, it can be suppressed very rapidly, but it also stabilizes the long-range SCW at higher pressure. In contrast, the isovalent substitution of sulfur and telluride on selenide site works as chemical pressure, and it can control TS without inducing a magnetism. So we focus on the iron same sulfur and iron same telluride single crystals, and here is a combined and established phase diagram of these two systems. So first, let me share you what we know about these compounds. The color map here represents the intensity of nematic fluctuations evaluated by elastic technique. And the nematic fluctuations shows a Curie-Weiss type divergence, temperature dependence expected in second order phase transition. And Curie-Weiss temperature shown in these red circles approaches zero with enhanced magnitude. Thus, we can achieve a QCP of electronic nematicity with these substitutions. However, the change of TC around the nematic QCP is quite contrasting between these systems. In iron sulfur side, TC shows a sudden decrease at the boundary of nematic phase, But in ionosphere tellurides, the nematic QCP locates near the superconducting dome, and the TC is enhanced towards QCP. And this TC shapes a two-dome structure, and it indicates a distinct pairing mechanism. And indeed, NMR experiment says that in ionosphere sulfur side, the spin fluctuations is enhanced in parallel with TC. So indeed, so in sulfur side, the spin fluctuations are closely related to the pairing, likely closely related to the pairing mechanism. But in ionosphere telluride side, NMR experiment says that there is no significant spin fluctuations. So the enhancement of TC here is not originated from spin fluctuations, but it is rather likely driven by the nematic fluctuations. So distinct superconducting phases are further supported by the separation of these two domes under high field, and the nematic QCP of sulfur side is pushed outside of the dome. This suggests that the spin fluctuation is more dominant over the nematic fluctuation on the pairing mechanism. But in contrast, the dome of ionosphere telluride keeps straddling the nematic QCP until the superconductivity is completely destroyed. So this indicates that nematic fluctuations play a key role for pairing mechanism in ionosphere telluride. Then I'd like to turn to the impact of nematic fluctuations on the normal state metallic properties in these two systems. In ionosphere sulfur, the Nigel groups have nicely found that the strange metallicity appears in the funnel-shaped region from the beginning of nematic QCP. So this motivates us to seek the strange metallicity in ionosphere telluride, in which the nematic fluctuation likely affects the electron pairing. So we applied the high magnetic field to destroy the superconductivity and try to see the normal state resistivity below TC. And here the field is applied in AB plane. So in this longitudinal configuration, the magnetic resistance is negligible. This is the data for X score 0.05, so with just small telluride substitutions. And the resistivity shows a T-square dependence expected in ferroliquid ground state below 5 Kelvin. And on the right side, I show the temperature derivative, and it becomes flat above the crossover temperature T star, and it continues to T1. So this corresponds to the crossover from the ferroliquid ground state to the T-near resistivity regime, increasing the temperature. So these behaviors are almost similar to the previous high field work of iron selenide. So the analysis applied here is, I believe, reasonable. And then we perform the systematic measurement in series of ionosphere telluride to see how this T-square and T-near resistivity regime changes with increasing X. And this is the obtained phase diagram and summary of this measurement. The blue region is a ferroliquid-like T-square resistivity regime, and the red one is the T-near resistivity regime. And as you can see, the onset of these two regimes is completely hidden below superconductivity. So, the destroying the superconductivity by high field is required for the proper discussions. So, for now, let's see the detail of this phase diagram. So first, inside the nematic phase, the resistivity follows the T-square at low temperature for all decompositions. And at X score 0.16, the onset of T-square resistivity is most strongly suppressed, so it has a wide T-near resistivity window. But this T-near resistivity regime in the nematic phase disappears with increasing X from this X score 0.16. Then, and how does the resistivity changes across pure nematic QCP? For X score 0.48, which located just before QCP, it shows an anomaly around 5 Kelvin, and below that, resistivity shows T-square. And this anomaly likely points to the nematic transition hidden below the superconductivity. So again, while the resistivity inside nematic phase shows a ferrorelated like t-scale dependence, after crossing nematic QCP, resistivity shows a T linear down to the lowest temperature we measured. So away from QCP, the onset of T linear resistivity decreases, but it keeps following T linear. After entering antiferromantic order close to iron telluride side, the T-scale resistivity is restored at low temperatures. So we have found two T-linear resistive regime in the phase diagram. Both of them are observed at sufficiently low temperature, so this cannot be ascribed to the phonoscattering, so they can be taken as storage metallicity originating from electron scattering. And the first one is inside the nematic phase, but here we can clearly rule out that the nematic fluctuation drive this storage metal because it should be rather suppressed inside the nematic phase. Spin fluctuation might be a candidate for the driving source here, but it is unclear why T-linear resistivity is more stable at x equal 0.16. The origin of solid metallicity here remains open questions. And the other is outside of the nematic phase. The onset of T-linear resistivity, so T1, increase with approaching nematic QCP. So the leading candidate for the origin of strange metallicity here is enhanced nematic fluctuation at these low temperatures. And furthermore, the T-linear coefficient roughly follows TC. This points to the close relation between strange metal scattering with and electron pairing. This is quite similar to the case of hole-doped couplet phase diagram, which is already shown several times in these discussions, and also the electron-doped couplets. The important aspect of our observation in iron same telluride, I believe, is that the pure nematic fluctuation can also drive the extended strange metal regime. But this observation should be compared with iron same sulfur, which shows a classic quantum criticality. There are two key features. One of them is that the enhancement of T-square term towards the QCP, and the strange metallicity appears in the funnel-shaped region above QCP. But in the case of iron same towards QCP, but the strange metal regime is observed in the extended broad range rather than affirm. So obviously, this raises an question on the reason behind this contrasting quantum criticality. And one possibility I want to argue here is substitution-induced disorder.
2 minutes, Kosuke.
Okay. This is almost last slide. So and because the amount of substitution at QCP in iron same telluride is larger than iron same sulfur. This leads to the residual resistivity 1 order of magnitude larger than iron same sulfur. So this motivates us to consider a model of fermions coupled to the substitution-induced spatial random nematic interactions. This is similar to ones Ilya and Aavishkar discussed yesterday. So, but to the best of my knowledge, the exact calculations have been performed in case of antiferromantic fluctuations, but are not yet done for spatially random nematic interactions. However, as Ilya showed yesterday, this does not depend on the order parameter. So the spatial random nematic interaction might also stabilize extended strange metal regime as we observed in iron same telluride. And furthermore, this order interaction can provide a momentum relaxation mechanism in the metal coupled to nematic fluctuations. And iron same telluride Fermi surface is very small, and the Q equals 0 nematic fluctuations do not transfer large momentum. So it looks difficult to involve molecular process. But iron telluride has a multi-band character, so there might be a way to induce a molecular process. But again, the detail would be still remaining open questions. So I think maybe your time is a bit over, so I will stop here just showing the summary slide. And this work is under review now, and so I hope that it will be published somewhere soon. So thank you very much.
Thank you very much, Kosuke. Yes, very clear and beautiful data. So, are there any quick questions that for Kosuke, or alternatively we can leave it for the discussion? But I'd like to take, if there is anybody here, Moko, do you want to speak? Yeah, go ahead, Moko, and then Ilya.
I think muted.
Yes, he is. Moko, can you unmute? There we are.
In 0.5 and 0.8, where there is linear resistivity but t squared for x less than 0.5 and for x greater than 0.9. I mean, is there a kind of Fermi surface reconstruction at xc equal to 0.5 and around x equal to 0.9?
Okay.
I cannot hear clearly, so.
Okay, I think I got the question. So the question was whether there's any evidence for Fermi surface reconstruction around x equals 0.5 or around x equals 9, where the end of the antiferromagnetic phase is.
Reconstruction, I don't think so, because this is a ferrotype order, so it does not break translation symmetry. So there's no clear signature of Fermi surface reconstruction to the best of my knowledge.
All right, thank you. And Ilya, can you?
Yeah, thanks a lot for the really nice talk, beautiful data. I just have a quick question about this slide, and maybe I just missed it. So just below, 0.2, there does seem to be, there's features in this A2 coefficient. There's some kind of, pretty dramatic looking spike. And then something is happening, with this T-linear red region. It seems to be getting pinched down somewhere just below 0.2. So what is happening at that doping level?
It is again, it remains open questions.
Okay.
I'm not have a clear answer, but it would be an interesting topic to further investigation.
Cool. Thank you.
All right, thanks very much. Thank you, Kosuke. And let us move to the second talk in this session, which is given by Silke Bulpasha. And Silke, your screen is already there. So when you're ready, please, the floor is yours. Thank you.
Okay, thank you very much. So I'm taking the heavy fermion point of view here, as you can probably already guess from me drawing a point from where the strange metal emerges. Let me very briefly acknowledge a large team of collaborators and highlight only two. For the very most recent work I'll be presenting is Federico Mazza, my PhD student, and Shonak Biswas, a postdoc of the group of Fakir Assad. And we are right back here to our phase diagram of the strange metal emerging from a dot, a point in the temperature tuning parameter phase diagram. And that is, as I'll convince you, pretty much the story of the typical canonical heavy fermion compound. And one of these is ytterbium rhodium 2 silicon 2, which we sometimes call our poster child because it's so beautiful. And we can put its color-coded phase diagram right into this slide here. And it essentially looks like this. It's a little bit symmetrized, but it's almost this. Blue is Fermi liquid and exponent 2, and orange is strange metal exponent 1 in the electrical resistivity temperature dependence. So heavy fermion compounds, or not all, but most heavy fermion compounds can be made very pure. They are stoichiometric, they are single crystalline, and they frequently can be tuned with continuous tuning parameter, such as for this material magnetic field. And in that situation, I say the canonical situation is that strange metallicity arises from a point. I showed you the real data here without symmetrization. So you see this is the temperature dependence that all the data are fitted to across the temperature ranges for different magnetic fields. And then if the exponent is 2, you see blue here. Interestingly, even the blue is interesting. The A coefficient of the t-square resistivity is very strongly enhanced when you move towards this point here. That means that the effective mass appears to be strongly renormalized towards the critical point, up to the point that it is consistent with a divergence from both sides of the quantum critical point. That's not only true for the A coefficient, but in heavy fermions, we very frequently have this similarity, or the Kadowaki-Woods and Sommerfeld-Wilson scalings. So that means the specific heat and the Pauli susceptibility follow precisely what the Sommerfeld coefficient, what the A coefficient of the resistivity is doing, and that's shown in this inset here. So then if we are looking at the orange, that is where the resistivity is strictly linear in temperature, and that's our strange metal. So what is there else in the phase diagram? Indeed, there is a Néel transition. Yet we argue that this is not what drives the strange metallicity. So it is a quantum critical point, yes, but it is not. The strange metal fluctuations, as we believe and realize more and more, are not only created by the presence of this order parameter. For instance, the theoretical description of the order parameter criticality cannot, in a clean system, give rise to linear and temperature resistivity. So we think that the order is more a consequence of this critical point here than the driving force for everything. Just to show you that color-coded data have real meaning. So this is the actual resistivity data shown in different scales, because linear resistivity is only shown on one order of magnitude in a linear scale. So I can make several of these plots. That means overall, this linearity actually spans over orders of magnitude. So this is more than 3 orders of magnitude linear exponent within an error bar of 5%. A very quick word, as it was discussed yesterday, about Planckian, yes or no. So this was a plot that was already discussed. We reinvestigated it. It was from quantum oscillation, meaning large fields. And heavy fermions under large fields are quickly driven away from the quantum critical point. If we take the data from resistivity, where we can look at the entire range of renormalizations, we actually get a slightly different picture. So this was the alpha equal 1 line. We reinvestigate heavy fermions with transport to extract the coefficients that we need in addition to the A prime. And we see that the closer we get to the quantum critical point, this is always the closest point to the quantum critical point, the lower that alpha would be. So that means to us, it doesn't look like, if we at least take the systems that are close to the quantum critical point, under that situation, there is no must to claim Planckian scattering with alpha equal 1. So that's the questions that we had up, and I will focus on this one. What are the other experimental signatures beyond the linear T dependence and transport? Because it's obvious we have sort of different ways to explain or not explain linear and temperature resistivity, but maybe we should look at alternative signatures to really find out what's going on. And this is a cartoon here of what in heavy fermion systems appears as at least some characteristics. Whether they are totally universal is still to be found out. So in addition to this linear resistivity that goes along also with other non-Fermi liquid responses in specific heat, thermopower, many different properties, there is, if you look at the Fermi liquid that is adjacent to the strange metal, we see these enhanced or diverging effective masses associated with entropy accumulation, as I already showed to you. We have a Fermi surface jump across the quantum critical point. We have dynamical scaling in different properties. We have a loss of quasi-particles and enhanced multipartite entanglement, and probably many more that are not on my radar. And all of that usually leads to high temperature superconductivity out of that strange metal state. So let me just show you a few of these evidences. I think the Fermi volume jump is an important one, so I show it again, even though that was our first new signature in addition to linear and temperature resistivity. So across the phase diagram where this strange metal behavior is observed, we have a crossover in the Hall coefficient that gets infinitely sharp, meaning its full width Cepheid maximum extrapolates to 0 when we move towards 0 temperature. The interpretation in the Kondo language is rather obvious. So in a Kondo screen situation, the local moment contributes to the Fermi surface. It's a well-established theoretical statement. But if you break up the static Kondo screening on the other side of the quantum critical point, if you allow for that possibility, then the Fermi surface must jump because the local moments will drop out of the Fermi volume and the Fermi volume will be small. So this Kondo destruction transition is a natural way of visualizing why there should be a Fermi surface change. Then, of course, once you have freed your local moments, they can order. But it's a consequence of the Kondo destruction, and it's not the driver for all the physics. So that this is dynamic was investigated by the optical conductivity, or more precisely, the terahertz conductivity that became possible only after growing MBE films of this material, because this is precise only in the transmission without Kramers-Kronig transformation. And what was found is that the data can all be collapsed with this dynamical scaling analysis here, and the exponent of the temperature is 1. That directly links a linear in frequency response to a linear in temperature response if the other scale is small compared to either the frequency or the temperature. I have to stress that this is for an inelastic optical conductivity, so we had to subtract a residual, even though the scaling was almost as good as without the subtraction, but we were alerted to the need for doing this by one of our reviewers. And then we took that approach over to the beautiful data we already saw yesterday on LSCO. And when we also use that same analysis, we here means Xingwei Li from the group of Jun Kono, we actually did this analysis, then a very similar scaling could be found here. And I'm sure you have many comments on it, and also that linear in frequency dependence is directly seen at the lowest temperature that were available in this study. There's another beautiful signature that speaker is strongly suppressed shot noise. Doug Nathanson will be speaking about this, so I skip it here. And I come to the result I want to spend a little bit more time. So that's a dynamical scaling in the inelastic neutron scattering response that we have very recently observed. It's on a different compound, and the reason is technical. We cannot make a terbium rhodium to silicon into large enough single crystals to have enough signal. So we picked something where we have a finger-sized single crystal, which is needed for these experiments. So you see the data here. That's the raw data, cleanly separated from any background and put into absolute values here with normalization procedures. And then we take these data and try dynamical scaling analysis that were already introduced much earlier by Almut Schröder, and there's also theoretical work on this by Chimiao Si. And we see that dynamical scaling relationship with now an exponent that is smaller than 1 is again found here over many orders of magnitude. So it's quite a robust scaling that is found here that would be consistent with this picture of Kondo destruction, where you have the clear idea of what this Fermi surface reconstruction means. So one thing that we did very recently is, I just wanted to show you this momentum space structure because we also discussed it yesterday. So that's really the typical situation we have at least in this compound and also in other heavy fermion systems where this local or Kondo destruction quantum criticality is seen, that this very low energy response, it's integrated from 0.15 to 0.35 millielectron volt, is really broad in momentum space. And the data that we show here are picked far away from any ordering wave vector and, of course, also from any Bragg peak. So we just go in the places where usually there would be nothing. So the last thing I want to show to you is that what we then did with these data is a so-called quantum Fisher information analysis. And this quantum Fisher information is, of course, a quantity that is well known to the quantum information community, because if you have a very large quantum Fisher information, you can do quantum measurements extremely precisely. So the larger this is, the smaller is the evolution of a quantum state that you can resolve. That's not of direct importance to us, but of direct importance to us is that we can actually witness this quantum Fisher information, or determine the quantum Fisher information by this relation here that was put forward by Peter Zoller and collaborators, where the quantum Fisher information has a so-called thermal filter function and then is directly related to the imaginary part of a dynamical susceptibility, which via the fluctuation dissipation theorem relates to our dynamical structure factor. So
2 minutes, Silke. Thank you.
Yes, I'm done. I'm almost done. So we do it, and what we find, so we analyze this quantity, and what we find is that it increases strongly as we decrease. So we at 10 is really the onset of the strange metal behavior in resistivity. And as we drive into the strange metal deeper and deeper, sitting exactly at the quantum critical point, this quantity shoots up. If we go at a field away from it, it stays small. So we can quantify it in absolute numbers, and we can conclude with a very modest assumption for our moments that we have in here, that we have at least a state of 9-partite entanglement. So this was also accompanied by theoretical work on the quantum Monte Carlo of a model that has this Kondo destruction quantum criticality, and very consistent behavior was found. So this is the picture that we come up with. We have this Kondo screen ground state on one side, decoupled local moments from conduction electrons on the other, and in the middle we actually have something that is quite surprising. We don't have a wide fluctuation between these two states, but we have something where the system can respond only as a collective to any temperature change or to any tuning parameter change. So it's something where the quasi-particles somehow perhaps disappear because of a collective that is formed. So that's quite a new idea. I think the thing I want to put forward here is, if we have these properties, the next talk will talk about the loss of quasi-particles, mine is about the enhanced entanglement. Maybe we should start to think of the electrons themselves as something exotic. So I feel that most of the community is thinking in terms of normal electron scattering of something, and the scattering being important. But maybe the concept of starting with normal electrons is just not the right one. So I'm done. Thank you so much.
Thank you very much, Silke. And yeah, beautiful data. Right. Any quick questions on this? Yes, we have Dirk raising his hand. Please unmute yourself and go ahead.
Yeah, Silke, beautiful talk, beautiful data. When you showed the ytterbium ruthenium 2 silicon 2, which is certainly not the first time I've been staring at that graph during a presentation or just reading it, actually I was struck by something I hadn't noticed before, and that is the region of linear resistance right at the critical point is really coming down like a delta function almost. And since the zero is quite a bit lower than where the measurements are, you know, it looks, I mean, to me this looks like a sharp region in magnetic field space, where you have the linear exponent and almost like a delta function, and outside there it becomes then immediately t squared. So I wouldn't even call that first order, but it's also not second order. It is something entirely different. Have you?
What's the question? What's the question? So that's what it is,
So
right? I mean,
yeah.
Well, I mean, of course, this is just a different exponent in the resistivity, right? That has nothing to do with a first order transition.
Yeah,
it's just
sure.
as close as I go. Maybe we see it best in this. Sorry, I think I have.
So it is very different from Subir Sachdev's original idea of it's more like a V shape. It's very far from that.
Well, I mean, look, from both sides, you can fit at very low. Of course, we have at very low temperatures. At very low temperatures, you see a T-square behavior essentially as close as you want to. If you just have precisely enough reached the quantum critical field, it's just a magnetic field, it's clean, right? You can go very close, and your A coefficient will be going larger and larger. Right, so that's the experimental finding. Of course, you should look at the real curves. I don't have the curves here, the original resistivity curves that will be straight, and then in some there will be at very low temperature this curvature over to the T-square. Right, at some point you can say, okay, so maybe we should zoom in. Right, you have to zoom in this graph. This graph is still
Yeah, and you're saying the color graph.
Yeah.
Yeah, of course, it's a color-coded graph, sure.
I think this is something we can carry on in the discussion session. Thank you. And in view of time, let's thank Silke again, and we move on to the next talk, which is Douglas Nadelson. Yep, we can see your presentation. Wonderful.
Thank you. Okay. Thank you, everyone. I want to thank the organizers for giving me the chance to talk to you today about this stuff. This has been a very interesting past, yesterday and today have been very informative for me. So Silke has saved me a lot of time. I'm going to talk to you today, I guess, as has been alluded to, I'm going to really go after question number 2 that we've been asked to ponder about whether there are other experimental signatures that could be interesting to look at besides linear resistivity. There we go. So again, super quick. I know we don't have a lot of time. These are the folks who really did the work. This work, the main part of what I'm going to talk about was published a couple of years ago. And we have something that's going to be coming out soon that is uncorrelated yet Fermi liquid materials as a contrast. And I think there's some lessons to be learned from those measurements in that system as well. So again, Silke saved me a lot of time. The system we're going to be talking about in particular in the experiments is a terbium rhodium 2 silicon 2. I don't have to explain to this audience again why this is an interesting system to look at. I do want to say one thing. The experiments we're doing, and there are technical reasons why we did it this way, and we are very interested in the future in going down into this temperature regime where, hang on, into this temperature regime where you can really see the field-tuned crossover from the Fermi liquid to the non-Fermi liquid, or the strange metal to the non-strange metal. But everything I'm going to show you on the experiment side was done at warmer temperatures up here, where this quantum critical fan is essentially expanded to fill all readily laboratory accessible magnetic field space. So everything I'm going to show you was in the strange metal regime. So what experiments can we do to see if quasiparticles exist? That was sort of my motivation for trying to work on this stuff. The thing I want to talk to you about, and I think the next speaker is going to talk about this as well, is shot noise. So shot noise was originally discussed in charge flow by Schottky over 100 years ago, who was worrying about vacuum tubes. And the idea is you can just ask, if I have a Poissonian source of electrons, there's just some average arrival rate for electrons in a system that's being driven out of equilibrium, I can actually do the statistical mechanics and figure out what are the statistical variations in the current, because the charge is coming in discrete pieces. And if you just talk about the charge current noise, the mean square fluctuations in the current per unit bandwidth, that ends up, if you do the Poisson statistics, that ends up having the form 2e times the average value of the current, where E is the charge of the electron, and the noise, as you can see, is frequency independent out to some cutoff that we can talk about if you're interested, but it's way beyond what we care about in these experiments. So basically you have white noise, and this is just for Poisson charges flying through space, and it's also a pretty good treatment for an ordinary tunnel junction. Shot noise is inherently current noise. It's a little bit of a technical point. In the experiments, we actually are measuring voltage noise and converting back into current noise using the differential resistance. And a parameter that shows up all the time is this thing called the phono factor, which is basically the ratio of the noise that you measure to the Poissonian result. Now, we're not going to worry about tunneling through free space or flying through free space. We're going to worry about a diffusive wire. This is a system where in the limit that was initially treated, it's a short wire. So we're going to assume that it's so short that the electrons do not have time to redistribute energy amongst themselves, nor do they have time to lose energy to the lattice. And this has some relevance to the discussions yesterday about energy loss mechanisms. I'll talk more about that. So you can get the answer in two different ways. You can take kind of a mesoscopic nanoscale approach, which is kind of the direction I came from originally in terms of my upbringing, if you will. And you can end up with doing a random matrix theory approach about a lot of different transmitting channels, and you convince yourself that the Fano factor should be a third. Um, a better, more general way to think about it in some sense is to ask what's the distribution function of the electrons look like in the middle of the wire. And what you find is that in the absence of electron-electron energy exchange and electron-phonon energy loss, the distribution function in the middle of the wire is some funny two-stepped thing, right? And if you go and you actually take the Boltzmann equation and you actually ask, what's the current correlations if you have this funny two-stepped non-thermal distribution function, you again get that the Fano factor is supposed to be a third. So if this technique, and this is kind of a theme with some of the stuff I'm pushing these days, this is something that has been looked at for a long time in the world of mesoscopics in ordinary weakly correlated metals. So some beautiful work was done 30 years ago where if you have a very short wire, you basically have suppressed noise because you have ballistic transport. If you're in this regime where you're below this electron-electron and electron-phonon scattering length, your Fano factor is a third. If your electrons are allowed to talk to each other and exchange energy to the point where they define some local electronic temperature, but they still haven't started losing energy to some other bath, then you end up with a Fano factor that is basically √3/4. And if you have sufficiently long wires that you really lose energy from the electronic system, the noise is basically suppressed. And the way to think about that is if the distribution function of the electrons looks just like the thermal distribution of at the lattice temperature, all you're ever going to see is Johnson-Nyquist thermal noise at the lattice temperature. So in strange metals at low temperatures, we usually talk about electron-electron scattering like it's a very strong thing. And we can have a long conversation, I got to be careful on the time, about the importance of phonons. This is a subtle point. I'll get to it in a minute. So the short version of this, leaving aside a lot of experimental details, which I'm happy to talk about, if I make kind of a mesoscopic little gold wire between big, thick gold pads, these need to be big and thick if I really want to make sure that I'm not seeing artifacts relating to heating of the contacts and stuff. You do find the noise versus the current, in fact, agrees extremely well with the theory expectation factoring in thermal broadening. It agrees very well with the theory expectation of 1/3. This is really the change in the noise away from the thermal noise. That's why these plots all start at 0. Yes, we can talk about exact functional forms and so forth if people are interested. Now, as you go up in temperature, and basically this Fano factor does start getting suppressed, presumably due to electron-phonon scattering. And I've got, we've another paper that we're getting ready to submit very soon to PRB, where I had a student look at wires that are quite a bit longer and, a range of lengths, a range of temperatures going way up in temperature to tens of Kelvin. And you really do see that the noise gets suppressed very strongly. The thing you have to be very careful about is you can be in an intermediate regime where the electron-electron energy exchange is present but not overwhelming, and the electron-phonon energy loss is present but not overwhelming. And basically then coming up with an analytic prediction of what the noise looks like is hard. You can basically be in some huge crossover, and it's tricky. So to get to the main point, thanks to Silke's and her group's amazing epitaxial films of this material, I had a very talented student where we figured out how to pattern the films without ruining their properties. Basically, the R versus T looks very similar to the unpatterned films. The magnetic field dependence looks very similar to the unpatterned films. So here's the little wire over here between two big pads. And the bottom line is you go and you do the measurements and you find that the effective Fano factor is really small. It's almost 0 at 10 Kelvin. And as I cool a bit more down to 3K, the Fano factor comes up, but it's certainly way less than a third, and it's way less than √3/4. And we saw this in multiple devices. And as I said, magnetic field doesn't seem to do much of anything to this beyond changing the resistance. Once you account for that, it doesn't really do anything. So it really looks like we're getting suppressed shot noise. Now you have to worry about phonons, right? So there's a way to deal with this. You can make very long wires, and you can ask, in the middle of a very long wire, you really think any energy dissipated by Joule heating has to eventually end up in the phonons. And you can play around with different phenomenological forms of this, but this is a standard one where you assume energy lost to sort of 3D phonons goes like T⁵. And you can go and you can do this analysis. And the bottom line is what you do is you take the Johnson-Nyquist noise in a long wire, and you look at that as a function of current, and the only fit parameter is basically gamma. And you can do this with gold, and you get pretty consistent gammas at low temperatures of about 5 × 10⁹ in these funny units. You can do this in a terbium-rhodium-2 silicon-2, and you get a gamma that's a bit higher. It's more like 9 to 9.5 × 10⁹, but the quality of the fits is good. There's only one adjustable knob here. Here's what the long wire looks like. So you can convince yourself, you can ask, boy, if that's the level of energy lost to the phonons, can that explain the suppressed noise? And the answer is no. You would need, if you just wanted to assume that you're able to suppress the noise by phonons, you would need a gamma that is 68 times larger than what is seen in gold. So we really don't think it's ordinary phonons. How am I doing on time?
You have 4 minutes, sir.
4 minutes. Okay. Right. So as Silke said, she put up this picture, which is from our paper. It's really, really tempting to think that the reason you don't get the usual Fermi liquid type response in the shot noise is that something really weird is going on with the quasi-particles. Empirically, the flow of charge is smoother and less lumpy than as a function of time than what happens if you have an ordinary system with either just non-interacting electrons or electrons that inelastically lose energy to each other so fast that they form some well-defined electronic temperature. So something peculiar is going on here. Now, I just want to take the last couple of minutes to talk about something recently that we've done. We've been playing around. We wanted to look at a material that is a strongly interacting Fermi liquid. And this is a terbium aluminum 3. This is grown by Kyle Shen and collaborators at Cornell. It's a mixed valence heavy fermion system. It's not super heavy. The effective mass is kind of 25 free electron masses. And the single ion Kondo temperature is quite high. In R versus T, it really looks like T squared resistivity, which we know is hard to see in a lot of systems, but T squared resistivity really kicks in below about 37 or 40 K. So we made some wires out of this stuff. Here's an example of an image of one of these wires. And here's again, the change in resistivity as a function of temperature between the wire and the film. And the key thing here is basically patterning it into the wire. All it does is it raises the residual resistivity sum. There's a magnetoresistance that's characteristic of actually sort of the bulk crystals of this stuff. But if you subtract off kind of this bulk-ish, linear-ish magnetoresistance, what you see is very nice weak anti-localization. You see these mesoscopic effects that you expect to see when you have well-defined quasi-particles. I just want to say, I mean, we're still working with Silke's group on this. I have seen no evidence of anything like this in YRS in this strange metal regime. So I think it's worth thinking about, can we use kind of the mesoscopic physics stuff that everyone decided was old and boring 25 years ago to check for the existence of well-defined quasi-particles, right? But we see weak anti-localization, we see universal conductance fluctuations. You can analyze the magnetoresistance to try and pull out some kind of a coherence length. And one last thing I want to point out in this system, which is interesting, you can do this long wire noise measurement to try and figure out the electron phonon coupling. And what we find is something rather bizarre. It really seems like first of all, the electron phonon coupling is big, and it's very strongly temperature dependent, even at these low temperatures where you think things are boring. And it turns out ytterbium aluminum 3 is actually quite tricky. It actually has a negative and temperature dependent thermal expansion coefficient in this temperature range that is not there in the non-magnetic analog. So there is evolving F hybridization going on with the conduction electrons, even though you're already in this limit where you think you've got well-defined quasiparticles. And so I just want to point out that like these issues about coupling to the lattice and how it evolves, I think they are subtle. And so you have to be very careful when you're evaluating things. So yeah, with that, I'll just end. I hope I've persuaded you that shot noise is a potentially useful thing for looking at another angle for looking at whether there are well-defined quasiparticles in the strange metal phase. I think looking at the a strongly coupled Fermi liquid, this particular example tells you that you really do have to be very careful about these issues about energy loss to the lattice. And again, a sales pitch. I think maybe we can think a lot about whether mesoscopic effects that we think we already understand in ordinary metals, can they be interesting probes of non-Fermi liquids, right? I mean, what are the long-lived excitations as you get near T equals 0 in these things that don't seem to be Fermi liquids? There's got to be something. We can talk about how incoherent quasiparticles are, but that just means that that's not a great basis for thinking about what the long-lived excitations are. And with that, I will stop.
Wonderful, thank you, Doug. That's fascinating. Right, we have time for a couple of quick questions. If you'd like to raise your hand. I mean, I just have one quick question. You say it there in blue, not black and white, but in blue and white, about the aim to go to lower temperatures in YRS. Because I mean, I'm really impressed. You've got your system working down to 0.2 Kelvin. I mean, so it's the obvious question.
The transport measurements are down to 0.2 K. The noise
I
measurement.
thought the shot noise was 2. No.
No.
Okay. So
now Silka has a terrific system for doing the measurements, but the actual, like, there's some real subtleties about sample fabrication and really making sure that your contacts are not. I mean, there's 0th order things about whether contact resistances are a problem, but there's even more subtle things than that. Because if your contacts are basically big, ordinary Fermi liquid metals, you need to think a little bit about what's the actual effective size of your wire, right?
Yeah.
And so I think it's a tricky thing that we're still working on this.
Apologies, I think my audio is creating noise, so I'll mute as much as possible. All right, Aavishkar.
A very nice talk. So in the last slide, were you trying to say something along the lines that the F electrons, the heavy electrons, somehow renormalize the coupling of the electrons, the conduction electrons to the phonons? And that.
So in the ytterbium aluminum 3, what we think is essentially yes, but in like the crudest possible way. So basically the density of states at the Fermi level is still evolving with temperature. And essentially the electron phonon scattering rate is related to the density of states at the Fermi level. So that's in that system, that's the subtle bit.
Very quickly, Peter.
Sure. One quick question. This gamma factor that you spoke of in the beginning, what's it related to in terms of other things that we know? Is it is it a measure of the electron phonon coupling constant, like this dimensionless?
Yeah. So I think
speak of lambda. So what do we know about that number? Is it a normal number?
So if you want, I can point you to a terrific RMP about this sort of thing. So basically, yeah, the electron phonon coupling constant is in there, and it is writing the equation that, like, there's a way to write the equation where the connection to lambda is more close. But yeah, it should be directly proportional to the usual electron phonon coupling. And again, the T to the 5 is making an assumption about that the phonons are 3D, and it's making, you know, honestly, the T to the 5 kind of assumes that you basically have a Fermi liquid coupled to, or a Fermi gas coupled to kind of a T cubed phonons, right? So you have to be tricky. You have to be careful. If you have a non-Fermi liquid, you do have to be careful in how much you trust that. Yeah.
All right. I think we should move on. Thank you again, Doug. And we move to the last talk in this session by Mindy. And please start your slides. Thank you.
Can you hear me?
Absolutely.
Are you able to see my screen?
Yes, we do.
Fantastic. Okay, thank you very much. And first of all, I'd like to thank the organizers, Nandini, Subhro, and Aavishkar for to be part of this interesting meeting. To me, lots of things are as a beginner, I'm learning many things and trying to digest many stuff. So what I'm going to talk about, the previous speaker already introduced this field, and it's made my life is much easier to go through. Short noise probing magic angle twisted bilayer graphene. Since this is the I think first time I'll be talking about. I mean, this is the first time we are talking about this twisted bilayer. So I'll spend some time. Before that, I'll just give you a glimpse of what we have been doing in our group. So we are a quantum transport group at Indian Institute of Science, Bangalore. So basically, we look at different kind of transport coefficients in mesoscopic systems. Mostly, they are based on 2D materials, graphene or twisted bilayer graphene. And we look at, for example, electrical conductance. Apart from that, also we look at which we have been mostly looking at the thermal conductance in fractional quantum Hall for anions and towards non-abelian anions and so on. And very recently, we started using the thermopower to probe twisted bilayer systems. And today, the topic which I'll be covering, the short noise to probe the magic angle twisted bilayer graphene. So as the name suggests, this is twisted bilayer graphene. So there's a two graphene sheet, and you give a relative twist angle between them. And as a result, so there is two things happen. One thing is that in the real space, you can create a artificial superlattice. And you have this momentum space also get modified. You have a reduced Brillouin. Most importantly, if you look at the band structure, they get completely modified compared to your singular graphene band structure. If you recall, the graphene band structure was a linear dispersance, but once you have this hybridization between these two layers, and for this magic angle, you have this isolated very tiny band, which is called a flat band with a width of few tens of MeV. And that's the interesting platform. The important number which I'll ask you to, or I'll request you to remember this, there's a number of electrons to require to fill this flat band. So there are total 8 bands. There are 4 conduction bands and 4 valency bands. And you need total 8 electrons to fill this complete flat band. So I'll be using this nomenclature, the filling factor. What it tells you the number of electrons required to fill the Moire unit cells. Although this flat band was predicted in 2000, I think around 2011 in this paper, although the continuum model, it tells you of only the metallicity of these systems, but I think the surprising thing came in 2018 by these two following paper. The first paper, it was shows that when your Fermi energy in your flat band, in the middle of the flat band, where you have the largest density of states, where you expect the largest conductance, in contrast, what was shown, the conductance goes to 0. And this was the first dramatic effect that this is the correlation or beyond single particle physics is happening. So the many body physics are placing a role. And not only that, but subsequent paper, I think they were in the same volume. It was shows that this system also shows the superconductivity around this half filling. And since then, there have been many experiments, and the different kind of experimental technique has been used to understand these systems are following. For example, resistance measurement, like these are like a global transport, like thermopower, which we have been using thermopower in our the twisted to understand the twisted bilayer. In fact, Nandini and many of our colleague here, Sumilo, we are using to understand these systems. And there are many local probe also has been used, like scanning tunneling spectroscopy, compressibility measurement. Recently, quantum twisting microscopy is very similar to like RPS measurement to understand the sort of the dispersion of the systems. And what is turns out that the system, of course, many body physics are important. Also, the core topology also is taking place. That's sort of the right now the scenario. So what I'm going to talk today, because I'll be using this like previous speaker, the short noise to probe these systems. So before that, what are the big questions about in this twisted bilayer graphene? Yeah, of course, the big question is what is the origin of superconductivity? That is sort of a holy grail nobody knows, and that's something we want to understand. And but beyond that, I think which can be answered. For example, what is the pairing symmetry of this superconductivity seen in magic angle twisted bilayer graphene? What are the charge quanta in the systems? And most importantly, the metallicity has been seen around the superconductivity dome. That which is the linear resistivity, which is very similar to which has been has been proven so far from the resistance versus temperature measurement. They are like a strange metal. Can the short noise can shed some light on these topics? So just to give you just a glimpse of what is known about the superconductivity in twisted bilayer graphene. Of course, the zero resistance has been seen, the coherence has been seen, the Shapiro step has been seen, and but most importantly, the tunneling spectrum in STM and the superfluid stiffness measurements and Andrip spectroscopy, they confirm that the superconductivity in this system definitely unconventional or non-BCF type of superconductivity, and most likely they're like a POF kind of superconductivity in these systems. However, there is no probe like what are the charge quanta using the short noise of this superconductor. The reason is there are papers which theoretically predicted that it could be 4e charge quasi-particle. So that's the superconductivity. What we know about the linear resistivity. So this came the linear resistivity following this paper, and this paper covers not only the magic angle twisted bilayer graphene, but away from magic angle twisted bilayer graphene, where even if you don't have a superconductivity, what was shown that resistivity is linear for large temperature scale, and what was addressed in this paper that this is probably happening because of this probably the electron phonon is the culprit, because you have a very small Fermi pocket and due to these Fermi surface reconstructions, and although the block Brunison temperature was predicted for this system of the order of few Kelvin, and after that there are paper, for example, this paper, Pablo, this was, I think the linear resistivity was so slightly lower temperature, I think up to 1 Kelvin or so, and the Planck, and they could show that in fact the alpha, it was bounded by this Planckian bound in this paper. And the most I think the most promising data what we have in the twisted bilayer community from this paper by Dima Efetov, and they could measure this linear resistivity up to 40 millikelvin. So 40 millikelvin to up to 2 Kelvin. So you can see the order of magnitude what they could see. This is sort of schematic of their phase diagram, that the linear resistivity can survive up to very low temperature, and this is probably the strongest evidence so far what we have the strange metallicity in these systems. So that brings down to what we have been working on, the short noise, and I think I'll skip this slide because the previous speaker already talked about this how the Schottky started to measure this granularity of these quasi-particles, and which tells you about the discrete nature of the quasi-particles. And I'll give you sort of like a cartoon picture. So what the short noise measure, basically what is happening, that you can think of like you have a tunnel barrier and there is a train of current which is coming from the left side, and you can imagine that because of this Poissonian process, there's a randomly sometime the electrons are able to tunnel, and imagine you have a detector on the right side is counting the number of electrons. If you count that, whenever the electron goes through your detector, there will be pulse of your charge, and that pulse arrival will be quite random process. So as a result, will be have a noise, and it turns out this Poissonian noise can be expressed the noise magnitude, which is basically nothing but the variance of your fluctuation, which is proportional to this the charge of the quasi-particle times the average current times the Fano factor, and this Fano factor is 1 for the Poissonian systems. However, you can think of like if you have the transmission is 1, for example, in this scenario there will be no noise because there is no fluctuation, because there is a current of the electrons, the detector will see there will be no randomness here. There will be the train of current will be constantly going through in the detector. But there can be scenario in the, you can hypothesize that somehow, if there is a scenario that instead of single electron, that there is a somehow bunching of electron happening, and they can only tunnel through if there is a 2 electron can tunnel. And you can see if there is a detector here, now you'll see the pulse. Of course, you will see a random pulses, but the pulse strength will be twice of the previous case, right? So this will give you the Fano factor 2. In other words, basically it can detect the Fano factor. In other words, in this tunnel barrier is basically detect that, the charge of the quasi-particles. And what you do in experimentally, you basically measure this noise strength as a function of current. At 0 current, you have this equilibrium thermal noise, and as you increase the current, you have this non-equilibrium short noise will give you, and the slope will give me the Fano factor. So for my talk, like the previous talk, the Fano factor is the most important. In the tunnel barrier case, you can have the Poissonian limit will be 1, and if you have a bunching of quasi-particle, like in the case of Cooper pair, it will be Fano factor 2. However, in a metal, for example, in a mesoscopic devices, the Fanos are much more complicated, which previous speaker highlighted very nicely. And so here again in the diffusive limit, for example, if you have elastic scattering, and it turns out that if your length scale of your channel length is bigger than your diffusive length scale, I mean if you have mean path is smaller than your channel length scale, you can show that the non-equilibrium distribution what you have that using that random matrix approximation and so on, and by bimodal distribution of this transmission coefficient, which using the Lander-Buttiger theory, you can show that there is a universal Fano factor. One can have Fano 0.33 instead of Fano 1. And interestingly, if you have, this is one scenario, but you can have various scenario. In the other scenario is that if you have a length scale, if you have a such that the electron-electron interaction length scale is smaller than your channel length, in that case, your non-equilibrium distribution which I was talking about, they sort of thermalize. The electron bath is basically sort of thermalized, and you can have effective temperatures, and these electrons energy they are losing by the electronic thermal conductance through your contact, both side, left and right side. And in this scenario, you can sort of there is another universal value which can be which has been predicted, which is 0.43, and this is the summary basically. So interesting point is here what I'm talking about, the shortest length scale is not the important. Here the length scale, the channel length relative to your different scattering length scale, whether elastic mean free path or electron-electron or electron-phonon. So it turns out that for the elastic case or electron-electron interaction state, they are, there are 2 universal limit. However, if your channel length is smaller than the elastic mean free path, then there will be ballistic transport, and there will be again there will be no noise. So in this case, the noise will be suppressed. There's a other regime the noise can be suppressed. In this case, if the channel length is bigger than your electron phonon, then what I was talking about, this quasi-equilibrium hot electron bar, the hot electron will be losing energy to your phonon bath underneath your sample. The phonon acoustic, I hope the acoustic phonons will take away the heat, and that's the way the noise will be suppressed. It turns out okay, this is the single particle picture. These are the one to understand this thing. However, it turns out there are other ways to have the suppressed noise, and this is motivated by the previous speakers this fantastic work. And this turns out that there is a other regime the noise can be suppressed, and which is the strange metallicity. How am I doing? I'm talking
2 minutes, Nandini.
2 minutes. Okay. So this is the strange metal that if you have this quasi-particle description is fails, then you can have the the suppression of this noise. So that's motivate us to do experiment for our system. So this is the sample what we have. So what you see here in this system, there's a resistance as a function of filling factor of this flat band. What you see here, there are different part of the sample. So the middle part is, you can think of this like a normal Fermi liquid regime. The left side is the superconducting regime of our sample. You know, we characterize by the TC, by critical current, and so on and so forth. But let me go through the noise measurement. So if you start doing the noise measurement in the Fermi liquid regime, and so this is the noise spectrum look like. And if you try to get the slope of this Fano, it turns out 0.45. And not only single point, we basically look at throughout this normal Fermi liquid regime, and it turns out that system has throughout this Fermi liquid regime of this twisted bilayer, is this Fano factor is 0.43, to just to make sure that benchmark that we this is our systems are working really fantastic. I mean, their calibration of everything is working. In the same system, we basically look at other Moire system, which is HBN and graphene Moire. However, this system doesn't have any interaction physics. There is no flat band in this system, and the same measurement setup, everything remains same even in terms of device dimension and so on. We found the Fano is 0.33, which is the expected, because in this system the transport is the diffusive transport. The electron in length scales are much larger at this temperature. On the other hand, this flat band, since the electron interactions are stronger, so we see the universal Fano of 0.43 in these systems. So so after this, we look at this superconductivity regime. And once you start doing this, interestingly, what we see, the Fano is much larger than 0.43, and it turns out that in this case the data is qualitatively nicely can be described as Fano factor 2. And if you look at the throughout this superconducting dome, so this is the Fano analysis around the regime, that Fano 2 around the strongest superconductivity regime, and they drops down as you go closer to this Fermi liquid regime. And so most importantly, now the last part, so I talk about the Fermi liquid regime, the Fano of 0.43, and the superconducting regime, the Fano factor of 2. And now if you can do the Fano in the superconducting regime to make sure this is really the Cooper pair transport, if you do as a function of temperature, what we see, indeed the Fano factor decreases, and they become from the 2 they decreases and become same as below the critical current, above the critical current. So that makes sure that indeed the above TC the Fano factor reduces. So that's we basically confirms that really we look at the charge of the Cooper pair. Most importantly, the normal state above the critical current, if you look at this Fano factor, which we expect the Fermi liquid regime 0.43, we see much more suppressed Fano, which is close to 0.15. And if you summarize the Fano of the normal state around the superconducting dome and the Fano of the normal state, which I am calling a Fermi liquid state, there is a distinct, you can see the Fano is quite suppressed in the around the superconductivity regime. So the question is, why these suppressions? So is it a strange metal or is it electron phonon coupling? We did exactly the similar analysis like the previous speaker mentioned about it. And so in this case, of course, this 2D system we have used. So we have used this T square, so the T to the power 4, this model. And it turns out, if you want to explain the suppressed Fano in the normal state above the above the critical current in the superconducting regime, you need the gamma. In this case, the gamma is just a proportional to electron phonon strength. Also, it involves some other parameters. It turns out in the same system, to explain the suppressed noise, you need at least orders of magnitude larger gamma compared to the Fermi liquid regime. So that probably tells us that is probably strange metal. And I can tell you, okay, that's brings us to our concluding slide. We are now repeating in one more device. Some part of the result, we have already repeated, and it is ongoing. And thank you very much for your attention. I'll be looking forward questions and comments. Thank you.
Thank you very much, Aninja. Fascinating stuff. Okay, that's beautiful work. Are there any quick questions for Aninja before we move to the discussion session? Of course, you can always raise them. I think Doug has a comment.
Thanks. Super quick. I think I may have asked you this at the APS meeting, but I couldn't remember. So in the regime where you're seeing the 0.43-ish Fano factor, how long is the device? Like, what's the spacing between?
Right. So the device length is around 5 to 6 micron. Right.
Okay. I mean, I guess the real question is, what do you think the electron inelastic energy transfer scattering scale is.
Right. So yeah, I think so. We just had an estimate about this. I think this slide tells you about the estimation. So I think the important parameter is because the Fermi velocity is computer graphene based systems is almost like a 2 orders of magnitude smaller. So that actually, because it is flat band nature, so that brings down the electron length scale much smaller compared to the conventional graphene system. Yeah.
Thank you.
Yeah.
Okay, thank you very much to all the speakers. That was a fascinating session of talks, some great talks. I think I was asked just to give a very brief summary before we kick in with the discussion session. So I think, clearly the main message from this, well, there was a few messages, but from Koske's talk, that we, in contrast in the chalcogenide systems, so this was a non-cuprate session, of course, we looked at chalcogenides, heavy fermions, and then the twisted graphene. And in the chalcogenides, in contrast to the sulfur-doped iron selenium system, there was this extended range of T-linearity in the tellurium-doped system, and that was coincident with a much greater residual resistivity. And so one of the points put forward by Koske was indeed that it was the increased disorder that was giving rise to that extended strange metal regime. And I think that was, kind of point was driven home by Silke in her presentation, that in a system with much reduced disorder, you get the singular QCP, mass enhancement, Fermi surface reconstruction, dynamical scaling, everything. And I think the second message to come out of Silke's talk was the encouragement to think about these charge carriers as something quite different, and of course that's the exciting part that we should go looking for, as opposed to, say, some anomalous low energy scattering of more conventional quasi-particles. And that theme was continued through with Doug's presentation on the shot noise, where you really see a manifestation of some new type of physics, and I think they were very careful to rule out perhaps more mundane explanations for that. And I'm sure I can imagine that those arguments were honed through the review process of that very paper. But then you showed, now in the interacting Fermi liquid system, that even there, you have to be very careful to disentangle the points. And that brought us very nicely onto Aninja's presentation on the twisted graphene, where the Fano factor was varying a lot in the system, but it seemed to be reaching values which were sort of consistent with Fermi liquid regime, with the superconducting regime, and then tantalizingly suppressed in the T-linear regime as it was in YRS. And so, there was also, we should say, an extended region of low temperature T-linearity in that system, and again we perhaps need to inquire about the level of disorder that manifests itself in these twisted bilayer systems. All right, so I think that hopefully gives a snapshot of what we've just heard, and I'm happy to open the floor to comments, questions on those topics. And I'll try and mute myself because I hear I'm creating a bit of background noise. I saw in the chat there was a question. Oh no, and we have a raised hand. Is it Dan? Let me just see. Sorry, I've got the chat open. Oh yeah. So Suvik.
I think we have Krish was also asking a question. You need to unmute yourself.
Hi, am I audible?
Yes, you are.
So my question was about the residual resistivity. So in general, to the transport people, is it expected in the strange metallic phase, the residual resistivity would be higher than the Fermi liquid phase, for example? So especially to Professor Silke, who has seen this linear entry resistivity up till, I saw the data up till 30 millikelvin. Do you see it saturating in some places it is saturating below some temperature. And like, what can you say about that residual resistivity in comparison to the Fermi liquid state?
So I think that was a question for Silke, I think.
Yeah, someone always has to take the unmute button. I would have replied much earlier. So in the ytterbium rhodium to silicon 2, there is no enhancement of rho 0 associated with going to the quantum critical point. It's actually pretty featureless. If you measure at the very lowest temperatures, we have this crossover-like behavior of the resistivity and thus also of the residual resistivity, because at the lowest temperature, you are essentially dominated already by the residual resistivity. And it just does a little bit something similar to the Hall coefficient. So it has a small in absolute value, but continuous crossover from one side to the other side of the quantum critical point. And there is never an enhancement or something at the quantum critical point. I know that exists for some materials, but not for this material.
Right. Yeah. For example, twisted, we have seen that the residual resistivity in the quantum critical phase is actually higher than the Fermi liquid phase. So, and
Yeah.
like,
Okay.
yeah. And from yesterday's Aavishkar's talk, I think he was mentioning about a smaller residual resistivity, if I got that correctly, for the spatially random interaction kind of model. So, like, it's a follow-up question to Aavishkar also. Like, do you think, I mean, can we say something very general about the residual resistivity to be higher or lower as a mark of the strange metallic phase?
I don't know. I think from what I showed is you can have a strange metal with very low residual resistivity. Now, you can always add residual resistivity by adding plastic impurity scattering. So,
Right.
so it's, I don't think like a strange metal phase has to have a residual resistivity, but it can.
Right.
Okay. Can I move to ask Philip? I know he's been waiting because he was muted for a long time. Nothing personal, Philip.
I won't take it personally. So I think I've earned the right to ask two questions. Doug, Silke, your experiments on the suppression of the fan effect factor show that most likely electrons are not the charge carriers. First question, is there an experiment you can do to figure out what the charge carriers are? And second, if you were to do an A-B type experiment, you punch a hole, measure the flux, that should give you the charge. Would you see, is there?
Oh, Doug is muted, so let me
Thanks.
start. So, yeah, let me start
Okay.
with, so one experiment we did is the inelastic neutron scattering, so to address it. And what we find is that the particles are entangled. So that would be one way of seeing it. If the electron is not an independent entity, but there is some kind of entangled state instead, then you would, of course, lose that particle nature. So that would be one kind of explanation. But I think Doug had another.
But all of
reply.
these are showing that you're losing it. I want to know, what is it?
Yeah,
So,
it's an entangled object. Don't think of an individual. It's an entangled, it's a
Right,
multi.
that's fine.
So,
But now if I were to do an Aharonov-Bohm experiment, punch a hole, do I see?
Okay. So Philip, here's I think this is a very important question. I know, I've been thinking about this a lot since we spoke about it before. So, conventionally, one would argue the usual in mesoscopic physics, the usual way of thinking about the Aharonov-Bohm experiments is in terms of coherent quasiparticles. And so the argument would be in the same way that there does not seem to be obvious like universal conductance fluctuations and things like that in the YRS so far. I think we need to look at that more carefully. Like that you would not expect to see anything, because if basically the Aharonov-Bohm physics is given by sort of quantum interference of quasiparticles going around the ring, if the effective coherence time of those quasiparticles is incredibly short, you won't see anything. That being said, I think Silke pointing out the entanglement question, I think I think there are some very interesting questions about whether if you did whether it's Aharonov-Bohm or if you did some sort of non-local resistance measurement or something
Right.
like that, right?
Right.
If you really think that there's long-range entanglement, can you get long-range things showing up in transport or in or in other probes where that are there even though if you tried to ask about individual quasi-particle coherence, the coherence length would be tiny. Right? I think it's a very interesting question. I think these are experiments that would be good to do, for sure. So I don't know what you would see. My initial reaction is you probably won't see any AB oscillations, because usually those come about because you've got some object that survives its path around the ring, right? If you've got some entanglement that somehow survives going all the way around the ring, then I think you should see something.
Yeah, and in principle, that kind of non-local transport measurement may in principle be easier than shot noise. So it's something that we should go for.
Yeah. That's what I was thinking. Since it's clearly some sort of non-local object, which I'm perfectly happy with, then in fact, we had talked about this a very long time ago.
Okay. Other comments, questions? Holikar, yes, please.
I'm still waiting. Yeah, okay. So I had a question for the theorists who are experts in short noise here. Is there a formal expression that connects that Fano factor to some correlator of the system? I mean, some correlation function of the system? I mean, like
yes,
analog of a Kubo formula? I mean,
yes, but you need to do some very complicated Keldysh calculation, and
yeah, that's fine. No, I'm okay with non-equilibrium correlation function, but I'm just curious to know what is that correlation function.
Yeah, you can look it up in Kamenev's book.
Okay, all right.
Yeah, it's the Keldysh quantum component of the current correlator.
Okay, all right. Thank you.
Yes, Mohit, you have your hand raised.
Yeah, I had a completely different question, and it's to everybody on this Zoom call, that in the cuprates, in addition to the linear resistivity, there was this tantalizing observation that the cotangent of the Hall angle goes like t squared. Now, in conventional sort of Fermi liquid theory, cotangent of the Hall angle is just 1 over omega c tau, and therefore it's also a measure of a scattering rate. And first question is to the experimentalist. Has this really been seen in a lot of other materials? I know that in twisted bilayer graphene, there is some hint of this, but I don't know of this cotangent, the Hall angle going like t squared, having been studied in heavy fermions or ion-based materials or other
Yes,
things.
it has. I mean, I think Yuji Matsuda's group showed the t-squared Hall angle coexistent with a T-linear resistivity in cerium, cobalt, indium 5. Also, the iron selenium sulfur system. I think also in the pnictide. So I think that there are examples of this across all those classes of material. So it isn't, appears, exclusive property of the cuprates.
I have a comment on it. Can you guys
yes,
hear me?
please,
Yeah.
go ahead.
So we have a recent paper which I think looks at this in terms of the optical connectivity, the cotangent of the Hall angle in terms of the optical connectivity. And I don't know to what extent people would agree with me, but I think at some level our data on this is on serum cobalt 5, again films that are made by the guys at Cornell, Kyle Shen and Daryl Schlamm. And so two things there, which I kind of, from my perspective, I find kind of incontrovertible evidence for two things. One is that linear T resistivity in serum cobalt 5 comes if you look at the width of the Drude peak. So the resistivity is linear in T. But if you look at the width of the Drude peak, it goes like T squared. So how do you rationalize that with a linear and T resistivity? Well, just quite obviously, the effective mass changes in a material like serum cobalt-5 dramatically. And it's, roughly 1 over, the mass goes roughly like 1 over T. So it's T squared and 1 over T, and this gives you linear and T. Now,
So
when
that
you look
is
at the
completely
potential,
different from the cuprates, right?
Yeah,
completely different from the cuprates. Yeah, completely different from the cuprates. Yeah, so this mechanism doesn't help you at all in the cuprates. The cotangent of the Hall angle is also, so we had a paper which appeared in PRB a year and a half ago on this. It suffered through the referee process, ended up in PRB, and I don't think anybody has seen it. We have a recent paper which is on the archive where, working with people at Los Alamos, we've done cyclotron resonance experiments in serum cobalt-5 out to very large fields, or large-ish fields, 30 Tesla, which is large, very large for optics. And there what you see is that the masses, you see a mass renormalization in the optical spectral weight. That was the first paper. You can measure the cyclotron mass from putting a large field on it and doing the optics under a large field. And you see that the cyclotron mass is not renormalized in the same fashion. And if you just take those two simple facts and you put it in and calculate the cotangent of the Hall angle, you allow these two masses to be different, you get the cotangent of the Hall angle goes like T squared. So, it doesn't solve any problems for us. It just kind of pushes our ignorance into different degrees of freedom. But, as far as phenomenology goes, I don't see any way that what we are saying in those papers is incorrect.
Okay, and it probably trying to put all these, as Dirk's points, raised, trying to put all these into the same basket is dangerous.
Yeah, so that's right.
Yeah.
So this is, and I don't think any of that works for the cuprates.
Okay, Philip.
Yeah, Nigel, can I share my screen? I just want to share a picture from the review article that you and I wrote.
I don't have that power. But somebody must have that power to give you.
Well, why don't you call it up and just show that figure? It's not a figure; it's a table which has all of the experimental properties, including cotangent of thetas of H, following T squared. And it shows all of the materials and the ranges of doping where that has been observed.
Yeah, hang on.
Right. You made that table.
Yeah, I'm not sure it's easily digestible in a quick
Well,
Zoom meeting.
In terms of what we want, if you look at the fourth column, it tabulates everything.
For those materials, indeed.
Yes, there you go.
Okay, so that's shameless plug to go and look at that table, is it, Phil? Okay.
Right.
So there's a lot more. So I think Nandini was next.
Yeah. So this was very interesting to see materials like cuprates, where the strange metal questions began, and to see it across different platforms. And I want to ask this question about disorder, which in the cuprates is inevitable, because when you scan doping, it also adds disorder. But these other platforms like twisted bilayer graphene and also heavy fermions may be much cleaner. So to what extent is disorder really important? Because in the theories, it's being invoked in an integral way. And it seemed that the very clean systems also had large regimes in parameter space where strange metal was seen. So the question is disorder essential, or these less or very clean systems give us pause for thought?
Silke, would you like to come in there?
Yeah, so I think maybe I shouldn't say that for another community, but I think there is quite some agreement that in particular twisted bilayer graphene is not clean, right? Because it's very hard So it's very disordered actually. So there are some ways to make it cleaner by screening and so on, but I think by itself it's not clean.
But
In the heavy fermion compounds that we have, when it's
Silke,
clean, it's a point, full stop. Yeah.
Yeah, Silke, one thing, but even there, the variable is not, X, which adds disorder, but it is gate voltage. So that is, not necessarily, it's for a given sample, and then you're looking at gate voltage.
Yeah, but of course, but still, you would smear out the relevant parameter behind in the system, I think. So that you cannot get a sharp, because each environment in the sample is a bit different. So that would create perhaps this overall deviation from a T-square resistivity.
So going to the noise experiments of Doug and India, my question is, at some level, in the noise is, if there is entanglement of electrons, if that is somehow important, was disorder disrupting it or aiding in the entanglement picture? That let me sharpen my question even more.
Yeah, so I think, okay, so what we know from our from the Fermi liquid regime, because the same, as you said, that is the same device, we just control with the gate voltage. So whatever disorder it is there in the Fermi liquid regime, probably the same disorder in the strange metal phase. So from the mean free path calculation, we know it's of the order of few hundreds of nanometer. That's typically the length scale, at least in our devices. This thing. So coming back to, so okay, I'm not expert on this entanglement. In fact, I have a follow-up question. Maybe I'll raise these questions. But if the entanglement has to be there, then probably it has to be the smaller than that length scale, whatever we are talking about. That it has to be smaller than the mean free path. Or okay, that clarity I don't have. But what we know, the disorders in twisted bilayer graphenes are of the order of few, and by the way, these disorders are not by vacancy of atoms or add atoms. These disorders are because of, as Selke was trying to say, is a because in the twisted bilayer graphene the disorder comes because of the angle inhomogeneity, because the systems are not uniform throughout the thing, so that can average out some effect, because the twist angle might be varying as different spaces of your sample. So shorter length scale, shorter width, maybe address those issues much more better way. But there is no not like the disorder in other system, like there are missing atoms or add atoms. So these are not known in the twisted bilayer, because these are graphene based systems, typically very clean. So the disorders mostly come because of this twist angle variation. That's I know. The coming back to this entanglement, my question was, the strange metallicity, we have the resistance, which means we have a joule heating, we have a dissipation. But if I see this non-locality and entanglement, then I don't know how do I see the dissipation and these two pictures together, because when I see the dissipation, it look like there are some sort of things are happening which is very similar to the quasi-particle description. So it's not clear to me. In the one hand, we are talking about the resistance of a sample, and there is a joule heating, I square R happening in the system. But on the other hand, when I look at in terms of non-locality and entangle kind of thing, how do I understand the same footage, the dissipation in that system? So this is my question to all theory colleagues, and yeah.
I mean, I think you have to be just coming at this a little bit from the kind of the mesoscopic side of things, right? Like you can have, I mean, it is true that if you really think of if the idea of entanglement is I've got some giant, an individual quantum state that's some huge superposition effectively, right? How you think about dissipation is tricky. But of course, if I have a manifold of states like that, you can imagine dissipation partly involving transitions between, like I don't know, maybe I'm not articulating this very well, but I mean, I can have, just even if you think about quasi-particles in a ordinary Fermi liquid, right? I mean, I can have things that show quantum interference over long distance scales and relatively long time scales. and I can still have dissipation.
So, but
Because there's a whole
dissipation,
manifold of states like that where I can where my dissipative process involves changing my how I'm populating that manifold of states, if you know what I'm saying.
yeah, but the mesoscopic, this, for example, ballistic transport, we know that dissipation happen at the interface, right? But there's not a dissipation at the in the bulk of my sample, right? I mean,
No, but I mean, I can make a little silver wire
Right.
where at 1 Kelvin the coherence length is the coherence length is a micron. The electronic phase is well defined for the quasi-particles is well defined over the distance of a micron, and I'm still getting some amount of I squared R heating per unit length in my wire, right? So I mean, I can still have dissipation coexisting with coherent phenomenon. I think it's a great question how you think about it if you really want to think about really rich entangled systems.
Thank you. Can I bring in Suvik, who's been waiting patiently to say something, then Subir?
Thank you. So I had a question for Professor Natilson. So you showed some very nice data on this YBAL3 gamma extraction from the short noise data. So like, do you have an understanding why this electron phonon coupling is actually increasing with temperature?
So yeah, sorry, I was going very fast there. So there just two things. One, I think the density of states at the Fermi level is still evolving even at this low temperature, which means, remember that this gamma parameter is actually, it's the energy loss rate between the electrons and the phonons. So it's not like the actual intrinsic, it's not necessarily saying something about the intrinsic electron phonon coupling. It may just be saying that if you actually do the sum of the total energy loss rate, it gets higher at low temperatures because the density of states at the Fermi level is getting bigger. There's clearly some weird stuff going on with the lattice in that material. Like the thermal expansion coefficient is negative below about 10 Kelvin, and it's negative and fairly strongly temperature dependent. So something funky is going on between, in terms of the interplay between the electrons and the lattice there. That's also that material also, by the way, at high temperatures, people have looked at it as a thermoelectric, and it's one of these materials where the phonon drag component to the Seebeck effect outweighs the purely Mott band component of the Seebeck effect. So like electrons and the lattice are really talking to each other in that stuff.
So,
Yeah, it's a strongly mixed valent system, right? I think you should say that, Doc. It's a strongly mixed valent, and mixed valent means it's coupling to the lattice extremely. So I don't classify it as a Kondo system. It's a mixed valent system.
Okay.
That clarifies many of these questions. Also, the strong coupling to the phonons, right? It's natural in mixed valence.
All right, thank you. Subir.
Okay, well, I want to make two comments on the things that I've discussed. One is that, people have been talking about absence of particles, no electrons, long-range entanglement, and dissipation. Well, I just mentioned that is precisely the features of, at least in a toy model, that you get in the SYK model, where you can really see how complex long-range entanglement and breakdown of quasi-particles leads to universal Planckian dissipation. Second, there was this question of disorder or not that people discussed. So it's worth mentioning there is a fairly quite solid theoretical result that if I have a bulk quantum phase transition described by, say, something like Hertzmiller's theory, then in the clean limit, that cannot give you a strange metal. I don't think many people agree with this. It's taken a long time in the literature to appreciate this, but it's something that has been known for some time. So then if you see a strange metal in a very clean system, what is the option? Well, I think there's still the possibility that there are degrees of freedom, like the F electron spins, that are effectively decoupled from each other. There is no direct interaction between them. And so really have to think about some kind of local criticality, or in other words, something with a flat band, which has lots of Umklapp. Those are all equivalence statements. I mean, eventually at some astronomically low temperature, maybe the moments start to feel each other in a more serious way. And when and why is that temperature so low is not something that we understand clearly today. Okay, thanks.
No, that was very helpful to comments, Subir. And Philip, I think maybe you can take the last word here, and we should move the floor to Nandini.
Okay, so on this, if Doug, you mentioned entanglement, and Subir mentioned entanglement in SYK. So I think you were talking about the fact that actually you weren't on that paper. Were you on the QFI paper?
Who?
Nope.
Okay. Zilka was.
Yes.
Yes. Okay. Okay. So I think given that from the QFI you can determine the depth of entanglement, so the number of partitions that the system that are talking to one another, that would determine essentially the length scale over which you would be observing some sort of coherent response.
At the time scale of the neutron scattering.
Yeah, at the time, yeah, that's right, that's right, that's right. But say you didn't do neutrons, which really only is probing the spins, so you were doing like Peter's experiment. That would certainly be a fairly good indication. The other thing is, Subir, do you have an estimate for the depth of entanglement in SYK?
Do I have an estimate? Not really. I mean, it's an infinite range model, but yeah, it has
Yeah,
volume law,
but
entanglement, entropy. But what do you mean by
so in
depth
other
of
words,
entanglement?
the depth of entanglement, in other words, if you were, so have you
Oh, I see.
calculated the
Compute the QFI?
Yeah, yeah.
Yeah. No one's done that, but I think that could be done. Yeah. Okay.
I think that could be done.
The
That would be
usual
very
QFI as
useful.
applied to a metal with electric susceptibility is infinite.
No, it's not. If
Sure
you
it is.
in a Fermi liquid, the QFI is incredibly small. In fact, the
No.
depth of entanglement is pretty much.
I mean, we have to be clear about what susceptibility we're thinking about
No, this
integrating.
is
But if it's
spin here, of course, in that case, right?
what's that?
I mean, in our case, it's a local moment, a spin-spin correlation.
Spin, yeah, right. So if you're thinking about the electronic degrees of freedom, then it's infinite because the susceptibility is
Yeah, but
finite in zero frequency.
No,
and
but
the
that's not
prediction
what the
from
QFI
Fermi
is
liquid would
probing.
also be.
No, we've actually computed this. It's in the paper in which we compared that with the cuprates, and it's a very different behavior.
Yeah. You mean you have to be specific about what susceptibility you're thinking about. So it's
The density response, not the spin susceptibility, not the
no, but
the thing you get from neutrons.
You're talking about calculating from the loss function? Yeah, so I think that's density in the sense.
The dielectric response. Yeah, that's right.
So but that's infinite in a metal for sure. Any metal.
No, but that's
yeah, anyway, I mean that's just okay, maybe we're getting off topic, but that's
right. Anyway, yeah.
Okay, well, I think we clarified what Silka's QFI meant, and I think maybe we still to clarify what is Philip's QFI statement. But I think it's good moment to bring Nandini into the picture, and please, Nandini, would you like to say a few last words or your summary thoughts?
Yeah, thank you. Thank you for these talks, for Nigel for sharing, and for the whole session. Of course, I was going to give you my theory for all this after hearing, a universal theory across all the materials and many different probes on the same phenomenology. But, given the short time, I can only leave my comments in the margins. But I know it's getting to be midnight in Japan, so I think at this point, perhaps the best I can do is to thank everyone, my co-organizers, first of all, Aavishkar and Subhro, and also all the speakers, the chairs, and all of you participants for coming on these 2 days for this very exciting experimental not experiments, but experiment of doing targeted questions on Zoom. And I also want to thank ICTS for hosting it, for Rajesh Gopakumar, who's the director, for encouraging us to and finding a time slot for us. And just for all of you to know, the recordings are available. So, it was a lot of material. If we want to look at all these phenomenology later, that will be available. And that's it. We can.
Nandini, have you already shared the link for those?
The YouTube link has recorded the meeting, so you can just use that.
Yeah. Okay, and with that, I will end like the formal part, but since we are all here, the last part was supposed to be discussions on both days. So let's open it up and continue with discussions, and as people have to leave, that's just fine. But we'll see how that last part goes. Opening up discussions now for both days. So yeah, thank you all again.
And thank you, Nandini,
Thank you.
for arranging it. That's wonderful. Right, Aavishkar, I think I'll let you take the floor.
Yeah, well, I mean, I just want to get back on this thing about like the clean systems versus disordered systems, and of course, YRS is very clean, and that could imply, as Subir said, that the F electron band is just so flat that it just has a lot of umklap, and it serves as the momentum sink for electrons. Is there do we know how flat the F electron band is? What is the scale of the bandwidth in YRS?
So as I showed, I mean, if you want to estimate the scale of the bandwidths, you rely on a Fermi liquid picture. I mean, you can try to rely on a Fermi liquid picture and get the effective mass enhancement, right? And that diverges. So the band gets infinitely flat at the quantum critical point, which means nothing but that the F electron localizes, right? In the ultimate limit, that's what happens. So you localize the state. It's an orbital selective Mott transition, if you will. That means the bandwidth of the F component is infinitely sharp at the quantum critical point.
Okay.
Yes, Subir, just please add.
Thank you. So a related question, which I think Aavishkar also asked in the chat. So when you go into the magnetically ordered phase, eventually there will be some correlation length of the magnetic order, or is it just completely independent? So what do you know about that?
Are you asking me, Subir?
Yes, Subir, yes.
So unfortunately, in the terbium rhodium to silicon 2, the magnetic order has not been detected by neutron scattering because it's so weak, right? It's the site. So it has been seen. We have an upper boundary by μSR, that's 0.04 Bohr magneton, the static moment, because it's so close to the quantum critical point. The critical field is only 60 millitesla, that we cannot go deep enough in the ordered phase to really characterize the order. But we know from other heavy fermions where it's a little bit more space in the phase diagram away from the quantum critical point, that the order can be quite standard, right? And that there you go to the ordering wave vector, you see your fluctuation, you see magnons, whatever. The ordered phase is not exotic, I think. It's just in YRS that is hard to study because samples are small, right, and you are so close to the quantum critical point. I don't think that there is anything really exotic about the magnetic state.
The features you mentioned of jump in the Hall coefficient and beautiful strange
that's
metal,
nothing
those
to
are
do
the
with the
best in
ordered
YRS.
phase. No,
Sorry?
it's nothing to do with the ordered phase that you see
Well, I
above
actually I agree with that.
Yeah.
So for example, could it be that in fact there is no order close to the quantum critical point on
No,
what
that's
you call the
no,
order
I
type?
don't think that's no, because I mean anything there is so specific heat down to very low temperatures and susceptibility, there is a thermodynamic signature of the order. So I think that is rather unlikely that there is actually no order. There is order. But it doesn't seem to
Could
be
be
a
some
play
order, but
order.
not magnetic order. I mean, it could be a more subtle
Oh,
type of.
no, but the susceptibility speaks a clear language. There's a clear kink in the susceptibility. I think it's obvious it's antiferromagnetic. It's really very low temperature magnetic susceptibility measurements, even down to microkelvin. So there is order.
Okay, thank you.
Yeah.
So the other comment I had, sorry, I just unmuted myself. Nigel, are you still chairing this part?
No, well, I thought you were chairing this session, but I thought now we would we can just jump in.
Because I wasn't sure. Okay, great. So my question was about how low in temperature can you go to see the strange metal? Because you have to suppress the superconducting state or whatever else is coming in the way. And we heard from Cyril in the first talk that they use magnetic field to suppress it. And then what was interesting about today's session is that in some of these other classes of materials beyond cuprates, it was much easier to go to very low temperatures compared to the cuprate relative scales. And then even see the crossover to T square. So you get a very clear idea of the strange metallic region. So I guess my question was about cuprates. Is there a way to go to lower temperatures somehow? And I also worry that the magnetic field tuning itself changes something in the process. Like we saw, it revealed a spin glass phase and so on.
Raj, I noticed Rajdeep has a question or has his hand up. I don't know if he's answering your question, Nandini.
Oh.
Hey, Rajdeep here. I had a question for the people who are doing the short noise measurements. Is there a version of what you do?
Rajdeep,
Sorry,
can I
oh, you had a question. Sorry.
Yeah, so mine was supposed to be a question, and
okay.
I didn't direct it to anyone in particular, but I
Okay,
was
sorry.
just
I was
waiting.
not.
Yeah, just waiting 2 seconds to see.
Yes, Cyril has his hand up, and maybe I'll say.
Okay, so sorry, I was mute. So it's a very good question, Nandini. Of course, we do our best to go to low temperature, but in cuprates, when you put 85 Tesla, so it's just impossible to do measurement in division fridge, unfortunately. So basically, we can go down to 0.5 Kelvin, but I don't think that we have ever done a measurement, for example, in LSCO at such high magnetic field and so very low temperature. So I see your question, and I see that for the moment we don't have answer for that. So maybe one of the key will be to use a FIB, focus ion beam, to miniaturize sample, try to avoid heating and so on. So find key to go to lower temperature. But yeah, it's a big challenge actually.
Yeah, one thing that's we are trying is to go right to the end of the superconducting dome, because curiously, when you go beyond the superconducting dome, you recover a pure Fermi liquid, pure T squared resistivity. So this T linearity doesn't just keep progressing, and it is striking how it seems to be very much tied to the extent of the superconducting dome itself. So the idea was for us is, of course, if you get down into the very much into the apex of that dome, then of course you can go to low temperatures. The superconductivity is very weak. You would need very small fields probably to kill it, and there we could explore hopefully the regime that you're talking about. And what's interesting as well there is, of course, you're still very far away from the putative critical point at P star. So you're far away from P star, but you're at the edge of the dome, and just where this this strange metal's kind of dying. And I think that's a region where perhaps we can look at that and answer your question, Nandi.
Okay, thank you. Zilke, do you have a point
I had
on
a
this?
question. I had one comment to that question. Actually, I digged out recently an electron doped cuprate, praseodymium, cerium, copper oxide, and their linear resistivity, because the TC is much lower. TC was there was just 12 Tesla static field needed to kill TC, and then the linear resistivity prevailed to, I don't know, below 100 millikelvin. So maybe one should also not just look at the highest TC cuprates, but go a little bit to old-fashioned stuff like the electron dope, perhaps. I don't know.
Right. Okay, thanks.
Yeah, that's a good point.
You're on.
Yeah, okay. So I had a question for people who are doing this short noise experiments and so on. Is there a possibility of doing a non-local version of the short noise like we do the non-local version of resistivity? Kind of thinking about the questions Silke was raising about maybe the size of the object that is actually carrying the current and so on, and whether if you have a non-local version of short noise measurement, whether that would be one way to have that kind of information extracted from that.
Yeah.
Nandini, you want to go?
No, so I can comment. For example, short noise is a 2-probe is a measurement. It's for even you can ask, can you do a 4-probe measurement? You cannot do that because the noise, the way, because it's a is a power. It's not just linear thing. That this is a power thing. So what you can what you take care of this, that you cannot separate out in fact the effect of the contact resistance also, right? So what I'm saying is that noise is because of this because it's a power, you just do the 2-probe geometry. So I'm not sure whether you can do any non-local. What do you mean by non-local noise in this case? Because the noise which is be created in the local part, they can also go through your where you are measuring your non-local probe in the sense of the conventional resistance measurement. So what I'm saying is the noise which is created in the local part, they can transmit to your non-local part in a conventional classical way and then contribute to the noise. So that doesn't mean there's a non-local noise. So that's the comment.
I agree with that. I mean, in principle, you could set up some multi-terminal geometry, and certainly when people play with edge states in the quantum Hall regime, and they can look at correlations between different. You can make a multi-port device that very carefully track. Yeah, I mean, so in principle, you can do that, but as Anindya says, you have to be very careful. And just if I just drove current over here and measured and looked at voltages over here, you may need to think very hard about how to analyze the data if you. Yeah.
I think that just to add to that, the quantum Hall, that's the beauty of the quantum Hall, because eighth state there is no scattering except the quantum point contact. So because of that, you can distinguish this sort of multi-probe noise spectrum. On the other hand, when you have a bulk is creating noise, is almost you cannot distinguish this different part.
I see. Okay. So there's another kind of noise noise experiment that has been actually proposed in theoretical papers a long time ago. That's bipartite fluctuations and test the scaling laws, area versus volume, to find out about entanglement. So there are such possibilities where you really try to see the size effect. But of course, it may well go to pretty small sizes. And then the question is, how to practically do it.
Yeah. Any other questions? I'm scanning. Chaitanya.
So I had one kind of comment and question related to the disorder versus, this question about disorder for the strange metal. So as far as I understand, in terms of what theoretical ingredients are needed. So as far as I understand, if you have a strange metal going down to T = 0, then and it's coming from kind of conventional electrons scattering off something, then I feel like the only two possibilities for the something are a disordered coupling to a boson or some kind of local scatterer, like Subhro was talking about. And if it's a local scatterer, thermodynamics kind of forces it to be a finite level thing, because otherwise you would have a residual entropy if you had local bosons, like in the omega equals 0 Holstein model that I was discussing. So it seems like those are the only two possibilities. You have local.
Say it again. Can you just say it again, Chaitanya?
I feel like you need some way to relax momentum at t equals 0, and the only two ways are disordered coupling to a boson or a local scatterer. And if it's a local scatterer, it can't be a boson, because then you would get a residual entropy.
Yeah.
So it has to be a local, finite level thing. So we might as well think of it as a local two-level system of some kind. And sure, there are experimental situations where that's kind of where that's natural, but just theoretically, those seem like the only options. And so the question is, well, and there are recent proposals from Steve and Erez and others about two-level systems, and Aavishkar has, in that work, there's some way that the models kind of naturally interpolate between these two possibilities. So it's probably quite interesting to think about experimentally. For a given system, can we just put systems on this spectrum? So I'm wondering if that has been done, or what experimentalists think about that possibility.
I think in general you want to avoid two-level systems. I mean,
no, but the question is the localizing moment, for instance, in the Kondo destruction setting, such an object, right?
Yeah.
Mm-hmm. Hmm.
I don't. What's a good model system for this? I mean, we in electronic glasses usually thought to contain some kind of emergent network of two-level systems. I don't mean like dielectric glasses, like was Doug Nadelson's PhD thesis. I mean like electronic glasses, like phosphor-stoped silicon, which is something we work on in a different context. On the on the insulating side of the metal insulator transition, there's this kind of emergent network of dipoles. That's the thing that absorbs energy if you're doing an optical experiment. But you kind of lose that as you go away to the metal side. So what's an example where you would kind of have this?
Well, it's tricky. I don't have a,
Yeah.
There are models you can write down.
Mostly
They're pretty far
hypothetical
removed from, yeah. I think that's
Do you have any predictions for that setting, right? I think if you have a clear idea what is a possible way to get the resistivity, can you come up with predictions that are beyond linear resistivity?
There's some papers on this. So I mean, I think Kivelson.
No, I mean in this case of scattering from a local.
Yeah.
So that's what I'm saying.
Erez and Steve and company have predictions.
But what is it? What are other signatures?
Linear and T resistivity with a coefficient
No,
close to
other
1.
than linear resistivity.
So
I mean, seems like linear resistivity we can get from. Yeah.
There was a famous work on thermal conductivity, very low temperature thermal conductivity in glasses if you had a distribution of two-level systems. I think that might have referred mostly to insulating compounds.
Yeah, but that's the two-level systems themselves. That's not my question. My question is, if you have electrons scattering from these two-level systems, what are the signatures beyond linear resistivity?
No, I agree with you. But if they're there would be a signature possibly in the thermal transport.
So one prediction of that would be what I kind of alluded to yesterday, was that you would get linear and T resistivity, but it would be coming from temperature-dependent elastic scattering. So you would see temperature dependence, which looked like linear and T, but measures of inelastic scattering would be largely absent or would just be flat in energy, right? It wouldn't scatter. So you would not get like omega over T scaling. you would not get, at least in the simplest perspective, right? You wouldn't get like what you see in the frequency-dependent scattering rate and cuprates. It looks, the scattering rate goes linear at omega. You would get a flat one. You would get elastic at any one temperature. The system would just look disordered. But that disorder landscape would change. That would be a prediction.
I think
Yeah,
that
but that's not
depends on
what's seen
how
in
it's
strange
coupled.
metals, right? There is energy over temperature scaling, as much as I can tell. So, and we can rule it out, right?
No,
As a
sorry,
wrong
just to
thing.
comment. I think that depends on how it's coupled. Like if you imagine the two-level systems just scatter more in their excited state than in their ground state, that's exactly what comes out. But if you imagine the coupling to the electrons actually flips the thing from one to the other, then you do get that's inelastic. So then you do get inelastic.
Just to be clear, when you're saying two-level systems in this context, you really mean the full Anderson, Halperin, Varma, broad distribution of everything kinds of two-level systems, or do you mean like some well-defined, like, they're all the same, which would be
The
could be
Anderson,
like what the F
Halperin, the Anderson,
yes or
Halperin, Varma like things. You need a broad distribution, otherwise you wouldn't get a T-linear.
I mean there would be I would think there would be funny signatures of long, slow relaxations and glassiness. Like I think if you really had tons and tons of two-level systems, I mean, I can tell you that if we I had a student spend a long time trying to fabricate devices out of for noise measurements out of 327 strontium ruthenate. And it would appear that whenever you etch that material, you basically produce an infinite number of two-level systems that live in the chemically unhappy edges of the material. And basically, in the noise case, the signature of these things being around is you see huge 1/f noise, because because of exactly electronic scattering off of some huge broad distribution of fluctuating two-level systems. So, I mean, I can imagine some kind of low frequency noise spectroscopy to try and look for these things. But it just seems like it's not there well, I don't know. I suppose it would be very interesting to look at like the cuprates, which we know are disordered because they're highly doped. It might be very interesting to look at the cuprates if you could really suppress the superconductivity in some nice way and look very low temperatures to see what you see. But
we are working on going to higher field. I mean, so there is maybe one proposal, one scenario where we can gain some information by going to high field. Is the one based by Kivelson and Berg and Cotter, where they use a two-level system as a superconducting puddle. And here, so the prediction would be if we go to very high magnetic field, so this puddle should disappear, so the T-linear resistivity. So, and this is something we are working on, but of course, this need to go to higher field to what we have today, and maybe for the future.
Yeah, so I think there's a question from Mukul.
Yeah. Okay.
Okay, I had one more thought to the question before. Can I put it?
Yeah, go ahead.
So because I was thinking in terms of your broad distribution of localized states, right? That you want. I mean, can they be dynamically generated? So what happens in this Kondo destruction scenario? That's at least what is in my mind. That at one moment in time, there is no screening and the F electron is there, but at the next moment in time, it's screened, and Kondo screening means that the energy of that local moment gets totally renormalized, right? If it's unscreened, it's the free electron energy level. If it's screened, it's a resonance at the Kondo at the Fermi energy. So dynamically, you generate that huge distribution of energies of the local state. I don't know whether anything like that would still work with your scenario, because yeah. So can it be in the time, can it be dynamically generated, the distribution in energy? Then I think heavy fermions are candidate. Otherwise, not at all.
I think that's good food for thought. Should I go to Mukul's question? Yes, Mukul, go ahead.
Yeah, thank you. I had actually one question for Dan Dessau from yesterday, and actually some thing which I wanted to ask in general, raise the issue in general. I mean, one is that basically all of the strange metals experimentally seem to show strange metal behavior and superconductivity at lower temperature scales around a point where there is a Fermi surface reconstruction. Okay, be it in heavy fermion materials or in iron arsenides or in cuprates, where a small pocket or a small Fermi surface, in a generalized sense, goes over into a large Fermi surface accompanied by loss of superconductivity. So there seems to be a one-to-one link between a kind of Fermi surface reconstruction accompanied by localization of a subset of electrons and a strange metal. So one of the candidates in that context is basically what Silke mentioned, is orbital selective Mott phase. And this is not a quantum critical point, but this is actually a distinct phase which exists over a finite range of parameter space. Okay. So the other option is, of course, to invoke intrinsic disorder in the exchange coupling in the manner of SYK Yukawa model, which also yields a strange metal phase. And so the issue is basically how would one try to reconcile, is it possible at all to reconcile these two apparently very different looking pictures? Okay, that's one. And the second was a question to Dan Dessau.
Oh, same. So don't you want to get an answer first? Let's.
Yeah, sorry. Okay.
This is already, yeah. Go ahead, Dan.
No, okay.
He has not answered.
I'll leave the question for Dan later.
Okay, save for me later. Okay.
Okay, basically, so thank you for the very nice talk. I mean, you showed that the exponent alpha in the power law liquid fit attains a value 0.5 around optimal doping and increases beyond 1/2 in the overdoped case and goes below 1/2 in the underdoped case. Now that is basically very, very interesting, but I have a question. So the question is that, I mean, one knows that when one goes to the left of optimal doping in cuprates, a pseudo gap opens up, an antinodal pseudo gap opens up. And one of the consequences of that is that the resistivity, for example, shows a dip from the linear in T behavior, okay, attaining T squared like behavior at very, very low temperatures. Okay, so the question was basically where the data you took somehow above the pseudo gap scale for underdoped samples, or how do you reconcile the fact that it is T squared at very low temperatures in the underdoped case?
Okay. Yeah. That's a great question. So when we're doing maybe there's two halves here. There's the ARPES portion. The ARPES analysis of these scattering rates, we're mostly focused just on the node. At the end, I showed you antinodal, but the scaling of this power law liquid, that's from the nodal states, which, nominally insensitive to what's happening at the antinode. There's weak scattering effects, but nominally insensitive. I did show one slide. Many more details will be coming connecting to the transport scattering rates, to resistivity scattering rates, where we were seeing the same exponent come off. All of that is above T star, exactly because of the same effect that you're talking about. So we actually find the T star in this self-consistent analysis that matches T stars from spectroscopies at the antinode. So I think everything is consistent there. As far as T squared behavior coming in the underdoped regime, we also find that's quite tricky. Any onset of localization physics, which is becoming quite important in the underdoped regime, it's an upturn in the resistivity, and it looks like a T squared if you just look at the curvature.
but the parameters, like the A parameters, etc., really don't match what you would expect for a Fermi liquid. So there's a cautionary note there to be really careful about if you see a T squared at underdoping, and more details will be coming about that.
So you are actually saying that if you kill superconductivity in an underdose regime, what you would end up with is a localized phase.
I'm not saying killing it like from magnetic fields. I'm just saying as you go underdoped, there's a lot of aspects of localization that come in that can affect how you might extract a T squared behavior.
Yeah, so doing the experiment.
But can I add something? Because in terms of transport, when you put a magnetic field in clean system like YBCO, under the YBCO, you clearly see a T-square at low temperature. We have many papers on that, on the mercury single layer also, underdoped.
Yeah.
So I agree that if you go very underdoped, I completely fully agree with you, but there is an intermediate region in the pseudo gap for underdoped cuprate where you do see a T-square at very low temperature.
Thanks.
Okay, sounds good. Any last comments or questions? I see Peter. No, Peter was just saying. Okay, so thank you all again, and hope there is some future for future discussions, a future meeting, and we can continue these discussions. So thank you all again, and for coming for both days, and wish you all a happy spring or happy summer.
Thank you to the organizer. Thank you.
Thank you.
Yeah.
Bye.